to introduce Rinku Chaudhary. She works as a AI/ML engineer in our company, and now she will guide us through the basics of the drug discovery and docking and the some concepts which will be needed for our hands-on session. So Rinku, please take over the session from here.
Yeah, thank you, Mahima. Yeah, so is my screen visible?
Yes.
Okay. So good afternoon, all. Now we'll explore how artificial intelligence is revolutionizing drug discovery through enhanced molecular docking processes. So we'll examine how AI algorithms are accelerating the identification of potential drug compounds by improving the accuracy and speed of protein ligand binding predictions, ultimately which will be reducing the time and cost associated with bringing new therapeutics to the market. So let us begin. Like, what is, as Dr. Islam sir already introduced, what is the drug discovery? So we'll quickly overview this. So drug discovery is the systematic process of identifying and developing new pharmaceutical compounds that can treat diseases or medical conditions. So here is the workflow where this complex journey typically takes 10 to 15 years and involves multiple stages. Like first, going for the research for what biological targets should be identified to the associated specific disease. Then then screen the thousands of chemical compounds to find those that interact effectively with these targets. The most promising candidates undergo rigorous testing for safety and efficacy, and also the traditional drug discovery faces significant challenges, including high cost, often exceeds around $2 billion per drug. So it takes lengthy process to complete, and also with only about 1 in thousands of compounds it is discovered, ultimately reaching to the market. So what is molecular docking? So there are few challenges in drug discovery in the pharmaceutical industry, which faces 4 critical challenges that make drug discovery one of the most demanding scientific endeavors. So the first one is astronomical financial burden. So for developing a single drug, as we said, it is costly. And then again, second, the extensive time requirements, which takes more than decades. And third, the lengthy experimental validation process, which requires extensive laboratory testing for animal studies in preclinical trials and clinical trials. And finally, the devastating low success rate, where only it shows less than 12% of drugs entering clinical trials, ultimately receiving regulatory approvals. So next will be what is molecular docking. So molecular docking is a computational technique that essentially acts as a digital matchmaker between drug molecules and their biological targets. At its core, docking aims to identify the best fit between molecules, specifically predicting how a drug or a ligand will bind to a protein's active site to form a stable complex. So think of it like finding the perfect key for a specific lock, where both the key and lock can slightly change its shape to achieve optimal fit. So the primary object is to determine the optimal shapes and relative positioning of both the protein as well as the ligand molecule, while minimizing the system's overall free energy. Essentially, finding the most thermodynamically favorable binding configuration. Success in molecular docking relies on two components which are critical. So the first one is sophisticated algorithms, and the second is the computational approach, where it requires scoring functions that can reliably rank and identify the most promising docking configurations. So here is an analogy, like molecular docking is like a log and key system where proteins are sophisticated logs with specific binding sites, and drug molecules are keys that must fit perfectly to stabilize the complex. But unlike rigid mechanical locks, both the protein and drug can like they can be flexible and adjust their shapes to optimize the fit. So in computer algorithms, test millions of possible orientations to find the best binding position for developing new medicines. So let me illustrate the transformative impact of computational docking by comparing it directly with traditional experimental screening methods. So in traditional assay, the throughput screening requires substantially financial investment, which is expensive reagents, sophisticated robotic systems, and experimental infrastructure. While in computational docking, we only need computational resources or software, so which reduce cost by order of magnitude. The time efficacy presents an even starker contrast where traditional assay can take weeks to months to screen compound, whereas in docking algorithms, it delivers result within hours or few days. So perhaps most significantly throughput capabilities differ dramatically. So in physical screening, the testing is limited for thousands of compounds due to laboratory constraints and resource. But in virtual docking, we can evaluate millions of molecular structures within shorter period of time. So the fundamental difference lies in predictive power, where traditional screening operates reactively, confirming binding interactions only after compounds have been synthesized. And in physical testing, there are often failures for late in process. In contrast, computational docking works proactively, predicting binding modes, estimating their binding affinities, and identifying the most promising candidates before any laboratory work begins. So this paradigm shift allows researchers to focus experimental resources on the highest probability candidates, dramatically improving efficiency and reducing the risk of costly late stage failures in drug discovery pipelines. So we'll be looking into different types of docking simulations. So basically, there are two types of docking. One is flexible docking, and other is rigid docking. And between the intermediate, it is semi-flexible docking. So in drug discovery, we use two main docking approaches, that is rigid docking and flexible docking. So in rigid docking, the protein is treated and is fixed at its position, like forcing a key into an inflexible lock. It's fast and perfect for screening thousands of compounds quickly, but it's not very realistic because in real life example, or we see the protein is more flexible. The protein and ligand are changing on the basis of the environmental conditions. So uh, similarly, in flexible docking, it allows both molecules to bend and adjust during binding, just like real biology. So this gives us much more accurate results, but requires significantly more computer power, and the like the resources is greater than for than that of rigid docking. So the choice is simple: use rigid docking for rapid initial screening. Then you may use flexible docking for detailed analysis of your best candidates. So let us go through the workflow of how the docking simulation is executed. So the molecular docking workflow allows it follows basically four essential steps. The first one is structure prediction, preparation, obtaining and optimizing both protein and ligand structures, adding hydrogens and charges. Then the second is conformational sampling, where it generates multiple three-dimensional orientations and poses of the ligand within the protein's active site. Then the third stage is scoring and ranking, where mathematical techniques are applied to evaluate binding affinity and stability of each pose, which can identify the most favorable configurations. Then finally, the validation stage, where top ranked poses are analyzed on the basis of biological relevance and experimental feasibility. So this system or the pipeline transforms raw molecular structures into actionable insights, enabling researchers to predict drug target interactions computationally before experimental testing. So we'll go with the first step of the docking, where we prepare protein. So the first step involves using, like, basically we can use multiple docking tools, but with this workshop we'll be going with autodock tools. So the protein is prepared using autodock tool, a critical foundation for successful molecular docking, where the process begins with importing the target molecule in the autodock tools. And then like the protein structure you may get from any data bank, for example protein data bank, and then follow the essential preprocessing steps in the hydrogens or assigning the partial charges, whether they are Coleman or Castigar. And then you may also need to remove water molecules that might interfere with binding predictions. Then finally, the prepared protein is saved into PDBQT format, which contains both the structural coordinates as well as the charge information. So after protein preparation, we go for ligand preparation, and also noting down the configuration file. So the second step focuses on setting up the docking tool such that it will read the ligand molecule, whether it is in any format, SDF, MOL2, or PDB. Then optimize its three-dimensional structure by adding hydrogens as well as charges. So it will also the Autodock tools automatically detect the rotatable bonds within the ligand, allowing flexibility during docking simulation. So similarly, as we save the protein file, even here the ligand prepared file is saved in .pdbqt format, and then as it will be also compatible with the Autodock Venom, which will be going further with the docking simulation. Then there is one more step which is critical, that involves creating the configuration file, which defines essential parameters, including grid center, its coordinates, that specifies the binding site location and the grid dimensions, or the where the ligand will uh, be docked. So this configuration file serves as the blueprint for the entire docking simulation process. So why this configuration file is important? As it controls the Autodoc winners, like it is the core file which controls the center. It tells the software exactly where to dock or where to look for binding by setting grid coordinates and search space dimensions. So basically, you can think of it as a GPS coordinates for your docking experiment. Wrong settings mean missing the binding site entirely. So if you get the config right and you get the meaningful results, you can like perfectly dock the ligand to the binding site. So even here, we face some limitations for traditional docking methods, where like the first one is inaccurate scoring functions. If a scoring function is not giving proper result, that may fail to accurately reflect like it will affect the binding site or the binding energy. Then there is limited flexibility, where if the protein is rigid, so we don't get real-time biology in there, and only the ligand is flexible. So instead of changing both protein and ligand conformation, it is only changing the ligand uh, its conformation. So also there is no explicit solvent or entropy handling, where in real-time environment, we add solvents or even other entropy contributions. But in docking simulation, there is also these features that are not been included or considered. So apart from traditional docking, we have saw that AI is trending and is transforming molecular docking in three key ways. That is, it is faster, which is using ML to predict binding in seconds instead of hours. Then smarter goals prediction by recognizing the patterns which traditional algorithm mostly sometimes misses it. And then continuation learning, where each experiment involves future predictions. So we can train the model on the basis of past docking results. So AI mostly involves scoring function. Even traditional involved scoring function, but we have saw that those are not so accurate. So AI-powered scoring functions uses machine learning algorithms, which are trained on thousands of experimental binding data to accurately predict drug target binding energy, which is replacing traditional physics-based methods with data-driven models that significantly improve binding pose, which is ranking and reducing the false positives in virtual screening. So in this workshop, for our workshop, we'll be implementing graph convolutional neural network. So it is a algorithm, or we can say a cutting edge machine learning approach, where it is designed for molecular data. It is capable of reading the molecular data. And so GCNs treat molecules as mathematical graphs, where atoms, you can see, uh, where atoms are treated as nodes and the edges are treated as bonds. So which creates a natural representation that mirrors actual molecular structure. So this architecture offers four key advantages. That is, the first is natural representation that captures complex chemical relationships. And then the speed. So it is uh, like it can predict 1,000 times faster than traditional docking. So if we include all the, or we can say, if we cover all the features which are required for predicting binding energy of a target specific data, then we can use this approach to make the predictions faster and evaluate the screening results. Apart from that, after docking, we mostly follow a few screening steps. So one of them is ADMET analysis, which is absorption, distribution, metabolism, excretion, and toxicity. So basically, this step is for predicting or calculating pharmacokinetic properties of a drug molecule as well as the physiochemical properties. So in our workshop, we'll be using ADMET AI tool. So it is a deep learning platform for comprehensive ADMET predictions. So it mostly covers most of the properties like bioavailability, toxicity, half-life, and also as it is trained on experimental data, so the accuracy is high, and the simplified version of input is Smiles input. So it is easy to run, and it is also the fastest tool. It is one of the fastest tool. So the workflow will be Smiles, then ADMET AI, like using the ADMET AI tool for analysis, and then we can reduce or filter it, the compounds data, by using specific threshold values, and then we can go further with the studies by selecting top drugs. Not, we can say drugs, but compounds. Yeah, so thank you for joining, and yeah, let's explore how AI is revolutionizing drug discovery. Yeah, I'm now happy to take your questions.
Okay. Thank you, Rinku. Thank you so much for explaining us the concepts for molecular docking and how it is done. So anybody has any questions for Rinku to ask anything? Okay, if not, I guess the meeting links for your hands-on workshop session is shared in your respective groups. So I request everyone to please join your respective groups, and there the hands-on session will be carried on. So yeah, you may leave and join another link. So yeah, Rinku, AIML tools for docking.
So like there is one deep doc, which is AIML based tool, which is always also mentioned earlier. Then there are diffusion based tools like diffdoc, which where we don't need to provide config file, it will automatically detect the binding site. So like there are mostly tools where we can also integrate traditional scoring function along with the uh, ML based scoring function. So there are hybrid tools such as GNINA. So yeah. Yeah, mostly flexible docking, like it involves only ligand flexible orientation, like only ligand is rotated. So protein is fixed in most of the tools. So that's why we are using AIML approach to capture all the features of the protein as well as the ligand and train it on the any algorithm.
Okay, any other questions? Okay. So yes, sir, should we start then for the hands-on workshop?
Yeah, before that, you may download a GitHub repository for workshop. So you can ping this link, the GitHub link. So you may download it from there, the data required for workshop beforehand.
So you are on mute, I guess.
So please join your respective group. I already shared in your respective chat.
For simulation, like till now, there is only AIML based technique is not so much involved in molecular dynamic simulation. So yeah, that is limited for traditional only.
Arthur.
Okay, so I guess we can go to our respective groups for the session. Yeah. Thank you, all of you. You can join the session.
After the hands-on session, you have to come back to the same link for the final session, and there will be a feedback form. So we will join the last session and fill the feedback form. We will be provided certificate. So please don't go anywhere. After session, you come back in the same link. If you have any doubt where to go, just let me. One of you from our side, please stay sometime here until unless everybody joining their respective group. Okay.
Okay, so hello everyone. I'd like you to download first the GitHub repository. So Hussaina, you may present the screen
Yes.
to show them how to upload. Yeah.
Yes, just a second. Yes, so I'll be sharing my screen. I'm audible, right?
Yeah, yeah.
Okay, so all of you will have to open Autodoc tools. So
And
this one.
Husena, you can tell them to from where to download the folder so that they
Okay.
might have the example dataset. Meanwhile, I hope everyone has installed the prerequisites like the software, as we will be doing traditional docking first and then move on to the ML based.
Okay, so the link given in the chat box, all of you can download the folder from there. I'm also pasting another link. The folder will auto download.
Oh, click on that. Yeah.
Yes, so I have pasted the link in the chat box. So there'll be a zip folder. You'll have to unzip that. And the folder will look like this. AIML workshop main. If you all can see on my screen, I'm pointing on that folder. You'll unzip it, extract it. So the folder will look like that. Once you open the folder, you'll find Autodoc Vina. So first we are going with traditional docking. So this Autodoc Vina folder is what we all will need for this first session. All of you should open it and check. There should be 3 files: the protein file, ligand PDB file, and the Vina exe executable. You all should check all these 3 files are there. Once you are done till here, please write in the chat box or let us know through your reactions so we can proceed further. Rinku, you can let me know,
Yeah, yeah.
and most
So
of them are done. We'll proceed further.
yeah. So let us know. Let's make this session interactive so we can uh, make the flow easy.
And for those who have downloaded the folder and you have checked the files, you can open 2 tools. One is Autodoc tools, which I already said, this one. And second is PyMol. You open it and minimize it and keep both of these tools.
Okay, so I hope everyone has done till now, like downloaded the required set. No need to open Vina, like you just need to keep the Vina exe file in the folder where it is already present, but you may have installed MGL tool. Yeah, so you can open it. The Autodoc tools you may open. No need to click on vina.exe file. We just need it in the working folder. Okay, yeah, Husena, you may start.
Yes, I can start, right?
Yeah.
Okay. So every one of you, first of all, once you open Autodoc, you'll have to click on File. Now we are setting the path so that we do not have to go on the folder again to select our files. So in File, you'll go to Preferences and Set. Once you are here, since my directory is already set, but for you, this path might be something else. You'll have to just double click it, delete that original one, and paste your path, which is the path of this folder. You can just copy this path, come back here, paste it, make default, say set. So this will be your default path. Once you are done till here, you can close this window. I'm waiting here for 10 seconds for you all to get till here. Rinku, let me know if
Yes, yes.
anybody is facing any problems. You can drop it in the chat box.
Yeah. I hope no one is facing issues. So you may ping if any error comes, or is there any difficulty?
Okay. So moving forward, once you have done this, you'll go to File. You'll say Read Molecule. Since you made that directory or parent directory, so you will see those two files, the PDB files, the protein PDB and the ligand PDB file. Click on the protein PDB. We are preparing the protein first. So click on it, say open. So the protein will load. So you can visualize it, you can rotate it to see its structure. If we talk about the structure, it is a homodimer. You can, on your left panel, where you see 3UE4, there's a plus sign there, which is for expanding and collapsing. So you click it, you'll see there are two chains, A and B. That is also visible here. There are two chains here, and both of them are exactly same. This is a homodimer. You can expand these chains also. With right mouse click, you can rotate it. With left mouse click, you can rotate it, and with right, you can move it. You can also zoom it with your mouse wheel. So once you have reached here, I'm again waiting for 10 seconds for you all. Anything, any error you want me to
Could
go
you,
slow?
Nilofer, could you like specify what second step, like uploading the protein, or you can unmute yourself? Yeah. So, Hussaina, could you repeat from where to upload the file, the protein file?
Okay. So you'll go to File, and you see this read molecule here. You have to click on that. A dialog box will open, and you can see the protein here. Click on that and say open. Okay, all of you have reached till here. So let's move ahead. So after your protein is loaded, we have two chains. This protein is a homodimer. So next step is we have to delete one of this chain. Since this is a homodimer, not a heterodimer, you can select any of the chain to delete. I'm selecting chain B. After selecting the chain, you'll go to edit. I repeat, you have to click on this box which says select, deselect chain B. Click on that. It will be turning yellow, which means it is selected. And you can see it here as well. After that, go to edit. You'll find a option called delete. You expand it, you'll see delete selected atoms. In delete selected atoms, click on that, say continue. Your chain B is deleted now. Rinku, let me know Everybody is here waiting
I
for
hope,
10 seconds.
I hope everyone has deleted their respective chains. So like at the end, you get only single chain so that we can use that chain for further process. Okay. Yeah, Hussaina, continue please.
Okay, so after you delete your chain, now we'll be deleting water. So again, go to edit and you will find an option here called delete water. Just click on that and your water, which is present in the protein in this chain, it is deleted now. I'm repeating again. After you have deleted your chain B or chain A, go to edit, say delete water.
Also, if someone is lagging, we have also provided Autodoc Vina manual within the folder. So you can also refer that for your future reference as well.
Yes. Shall I move forward?
Yeah.
So once you have deleted water, go to chain A, expand it, scroll all the way down. When you scroll all the way down, some of you might see it, some of you might not. So the last amino acid, which is ILE 502, expand it, scroll down, collapse it again. You will see this DB8601. This is our ligand. We'll delete the ligand. So click on it. This turns yellow. Scroll all the way up. Collapse A chain. Remember, you have to collapse it, else Autodoc might lag. So collapse it back. Go to edit. Delete. Delete selected atoms. Say continue. So now your ligand is deleted. I am repeating it once again. Once you deleted water, expand chain A, scroll all the way down. Since my ligand is deleted now, so it won't be visible. But after this last amino acid, ILE 502, if the ligand is not visible, you just expand this, again collapse this. So the ligand would be visible. Mine is deleted, hence it is not visible. But for you, it will be visible. It is named as DB86 something. Just click on it and scroll all the way up. Collapse this and go to edit, delete, and say delete selected atoms. And your ligand would be deleted.
Let us know in the chat box if anyone is facing issue.
I hope no one is facing any issues.
Yeah.
So let's move forward. So after that, again go to edit. And now we'll be adding hydrogens and charges. So we'll start with hydrogens. So edit hydrogens, say add. And we'll add all hydrogens or polar hydrogens, whatever you can. It's your choice. I'm adding polar only. Say OK. So once you add hydrogens, you can see hydrogens have been added.
If the recorded video will be streamed in the YouTube channel, so yeah, we'll be providing the recorded session as well.
Okay.
Hussaina, you can show how to add hydrogen atoms.
Okay. So once you have deleted water ligand, and then we go to edit, say hydrogens, and say add, and this dialog box will appear. Either by default, whatever settings are made, you say OK, hydrogens will be added, or you can say polar only. That's your choice. and again say OK. So hydrogens will be added. You can see hydrogens are added.
So basically we add hydrogens because to stabilize the complex, and also as they are, the hydrogens also involved in catalytic activities. So we are adding hydrogens to it. So let us know if you have reached till this point. Okay.
Okay, so we are moving forward. So again, go to edit. Now we are adding charges. So go to edit, say charges, and you can add Coleman charges or you can compute Gastiger charges. So I'm going with compute Gastiger. So you can see total Gastiger charge added. So charges have been added now. So I'm repeating this step again. Go to edit, say charges. Either add Coleman charges or compute Gastiger. Click any of these and the charges would be added. A dialog box will appear saying how much charge has been added. Everyone is here with me?
Yeah, it is fine, Nilofer.
Okay.
It is in the back end, like it will calculate the charge and will provide us the value, charge value.
Okay, so charges are important. Similarly, hydrogen are
So the
important
value
because,
may,
yeah, continue, Rinko.
yeah, to neutralize the structure.
Yeah, also because we'll be, post-docking, we'll be analyzing, and while binding energy, we'll be calculating, we'll be analyzing electrostatic, hydrophobic interactions. So these interactions will vary if we do not have charges, we do not have hydrogens, we don't remove water. So all these parameters are important for docking to correctly take place. So we are almost done with protein prep. Now you have to save it, but before that you have to convert it into Autodoc compatible format. So say edit, go to atoms and assign AD4 type. I'm waiting here on the screen. Say edit, atoms, assign AD4 type. Once this is done, we have to save the protein. The protein is prepared now. So I'm waiting for 10 seconds. Drop a thumbs up if you all are with me. Anybody facing any issues, let us know in the chat box.
Yeah, carry on, Zeno.
Okay, so now we'll be saving the protein. So on your toolbar, you'll be seeing this orangish panel which says ADT42, 4.2. Here you will see an option called grid. Click on that. We have macromolecule. Say choose. Here we have our 3UE4, which is our protein. Say select the molecule. Post that, our dialog box will appear, and if you pay attention, you can see the file will be saved as pdbqt, which is a requirement for Autodoc to run. The prepared protein file is saved as pdbqt file. So once this dialog box appears, say save. So your prepared protein PDB-QT file is saved. So here we are done with preparing the protein. Again, I'm waiting for 10 seconds. Anybody is facing any problem, let me know now before we go to ligand prep. I'm repeating the step again, how to save the file in PDB-QT format. Go to grid, say macromolecule, say choose. Here you will find 3UE4, which was the name of your protein. Select molecule. A dialog box will appear on your main working area. Say OK, and then automatically another dialog box will appear for saving the file in PDB-QT format. Save it.
So let us know everybody has prepared their protein and saved it in .pdbqt format. Yeah, go ahead, Zena. I guess there is no issues.
Okay. So now we are done with protein prep. Now we'll be going with ligand prep. So for that, everybody will go to the same folder where you had your protein and ligand files. You can see now we have the protein PDB-QT. Similarly, we want our ligand PDB-QT. So just go to the folder, right click, and say open in terminal. Once the terminal is open, you'll have to paste a command, which is an open babel command for preparing ligand. Rinku will be writing that command in the chat box. It will be also visible on your screens. So this is the command obabel hyphen ipdb, which is the input ligand file, ligand.pdb, output pdb hyphen h. Oh, output will be in pdb-qt. So it says opdb-qt hyphen h, and output will be saved as ligand.pdb-qt. So the output file name would be ligand.pdb-qt. You press enter, it says one molecule converted. So now your ligand is prepped. You can see that here you have ligand.pdb-qt. I can show that again. Once you have prepared your protein, go to the folder where you had your files saved, which was in AIML workshop, Autodoc Vina folder. You will see your prepared protein file and 3 other files, including Vina, ligand.pdb, protein.pdb. Right click, open in terminal. Here the terminal will load, and this command obabel ipdb, which is input pdb ligand file, output in pdb-qt format, and output file name would be ligand.pdb-qt. You have to write this command, say enter, and then it will prepare your ligand for you. And you can see that ligand.pdb-qt. Once this is done, everyone come back to your Autodoc tools.
So let us know once you are done with the ligand preparation.
Also, to give you exposure of Open Babel, we have done ligand preparation using Open Babel, but the same way as we prepared our protein, we can prepare a ligand also in Autodoc tools. So like we prepared a protein, similarly you can prepare your ligand and save it in PDB-QT format. Rinku, let me know. Anybody facing any issues, or when can I move forward?
Like till now, I guess there are no problems, so you can go forward.
Okay. So now again we'll go to grid. Once you are here in your Autodoc tools, go to grid, say set map types, say open ligand. In grid, set map types, say open ligand. Here we will find the ligand.pdbqt file. Click it, say open. So now your ligand is here. If you can see this, I have selected and highlighted it. Your ligand is present here with your protein. Once you are here, again go to grid, set map types.
Grid box.
You can choose ligand also, or again you can go to grid box. So I'm showing that again. Go to grid box. So now a grid box will appear here. So this grid box we have to center upon our ligand for it to calculate the dimensions, and then we can save it in a config file which will be utilized for running a docking. So now we are calculating the grid box size. So for doing that, once you go to grid, say grid box, this dialog box will appear, a grid box will appear. Here you have an option on the topmost side which says center. Click on that and say center on ligand. So your grid box is now centered on the ligand. And you can see the XYZ coordinates. And here the upper ones are the size of the grid box. And these lower ones, center grid box, coordinates are the coordinates which is from the ligand, its center distance from the grid box size. So XYZ coordinates of the ligand inside the grid box. Once done, say file, output grid dimensions file. This dialog box will appear and give a file name, say config, and save. So your config file with grid dimensions are saved.
Nilofer, you might have, if you have closed the Autodoc tools, you can upload the protein again. Okay. Yeah.
Okay. Once we are done with this, now go to docking, go to output and say Vina config. So the grid dimensions which we saved, we have to make it compatible. We are making the file compatible with Autodoc Vina. So here, after you go to docking output, Vina config, then you see a dialog box like this. And here you can see your input prepared protein, your prepared ligand, the grid dimensions, grid box size, and what will be your output post docking. So say save. Here we are just preparing the config file for docking. We have not started with docking yet. Say save. So once this is done, I'm waiting here for 10 seconds. Anybody is facing any issues, let me know.
Yeah, I guess it's going well.
Okay, so once we are done with this, you again have to go to the same folder where your files were present. Now you can see the config file is also present. This config.txt is the file that we'll need for a docking to take place. So once you are here in this folder, again right click, say open in terminal.
Yeah, Hussaina, can you explain the last step once again? I hope it's saving the config.txt file. Could you repeat it again?
Sure. So what I did is, after gridbox step is done, we went to docking tab in this toolbar. We said output, and in that we said Vina config. Then this dialog box appeared, and we said save. So yes, this was the last step.
So, Hussaina, you can open the config.txt file and show them how it looks.
Okay. So this is our config file. So you have the receptor, which is your prepared protein, ligand, your prepared ligand, center X, Y, and Z, which are your X, Y, Z coordinates, which you calculated when you centered the grid box around the ligand. And this is the grid box size. You can, you know, customize the grid box size according to how rigidly you want the ligand to move while you're docking. So this is the custom size which we are using here. And then output after docking would be ligand out.pdbqt. You can also change that, but we are keeping it like that. So this is what the config files looks like. So yes, going back. So once you come to the folder, right click, say open in terminal. You come here and you type VI, we are typing Vina, press tab. It will auto detect the Vina executable file. Say --config space, again write config tab dot txt. This is the command. Rinku, you can also paste this command.
Yeah.
And
So
say enter.
even if anyone is facing any issues in config.txt file creation, I've pasted the context. You can copy it and maybe create a .txt file.
So docking is running now. It will take 1 or 2 minutes. Meanwhile, you can ask any questions if anybody is lagging behind, time to catch up.
I hope everyone is at same step. If not, let us know. We'll help you out.
Meanwhile, for all of those for whom docking has started, you can open Pymol and keep. It takes 5 to 10 seconds for it to open, so just open it and keep. Okay, so we are done with docking. Here are the results. So Autodock Vina creates 9 poses by default. So the first column which says mode is actually the number of poses. So there are 9 poses, and these are ranked according to the best pose. The first one is the best pose, and the last one, which is the ninth one, is the last ranked pose. So here affinity, binding affinity is listed. So lower the binding affinity, better the pose. Then the next column is distance from RMSD, lower bound and upper bound. So this is with respect to the best pose. So when it is with respect to the best pose, so for first one, which is the best pose itself, it is 0. And for rest, it is calculated with respect to the first pose. So it has some values. So these are the RMSD values. Lower the RMSD values, better it is.
I hope
So,
everyone's talking is completed by now.
yes. So if this is done, you can close the terminal. And here you have your output ligand out.pdbqt, which is your dogged ligand. So once this is done, come to PyMol. I'm waiting for 10 seconds. And come to PyMol, all of you. Okay, let's move ahead.
Yeah.
So in PyMol, for those who have opened it for the first time, an activation window might appear. You just have to click OK and move ahead. Say file. Now we are opening our dogged ligand and protein. Say open. Now select the folder, the same AIML folder. Go to Autodoc Vina. Now first select your dogged ligand and also along with it, press Ctrl, select your protein. Say open. Oops, I guess I've opened the wrong thing. Just reinitializing. Yes, open. Open your dogged ligand and your prepared protein. Say open. Yes. So here you have your prepared protein.pdbqt and your doc ligand, which is ligand out.pdbqt file. So on your right side, there's a panel. You can see global frames here. You can see my cursor. So here are the 9 poses. You can play it like a movie. You can view them one by one. These are the 9 poses. The 9th one being least optimal and the first one being the best pose. So we have our ligand protein complex with docking done. Can visualize it, zoom it. Once this is done, we'll save this as a complex. So go to file, say export structure, export molecule. I'm repeating. After you have loaded your prepared protein and your docked ligand, which is ligand out.pdbqt. After it has loaded, you have viewed it, you can go to file, export structure, export molecule. Say save. Again, give it a name, say complex. And here you have to pay attention. It should not be PDBX MMCIF. It should be PDB. So save as type, say PDB and say save. Everybody with me?
Yeah, till now, if you have any questions or facing any problem, you can ask us.
Can you please share the protein that you have made after docking because I got some error in mine?
Yeah, okay. So Ananya, we have provided the sample data. So we can you can download it from there.
Okay. Is everyone here with me? So what we have done till now, let us summarize. We prepared our protein, we prepared our ligand, then we docked our ligand. After that, we visualized it using Pymol and saved the protein ligand complex in PDB format. This is what we have done till now. So we are at our last step, which is looking at the docked protein ligand complexes interactions. So how the ligand is interacting with the protein, what kind of interactions it has, be it hydrophobic, electrostatic, hydrogen bonds. So we'll be seeing that. So once you have reached till the last step, that is saving the complex.pdb file, you go to your browser, say plip, which is protein ligand interaction profiler. It is short for protein ligand interaction profiler. Say plip, and the first link which appears, which is TU Dresden University's link. So protein ligand interaction profiler, you open it. So you'll see the web interface. Towards your right, if you see my cursor, you see drop PDB file here. Either you drag it or you choose file. Here I have my complex.pdb file, which I saved using Pymol. Say open and say analyze. So here you can see, if you click on it, the structure will load in 3D. So you can again rotate it, zoom it, move it for better visualization. Yes. So here you have your 3D structure. So here they have given a legend which says all the blue residues which you see here are the residues from protein. The middle orangish thing which you see is your ligand. Then they have color codings for water, charge center, metal ion, if any. And then type of interaction, which is the hydrophobic interactions, dotted line. Then solid blue line is your hydrogen bonding. Then there is halogen bond here and salt bridge here. So it is giving you interactions. You can download it from here to visualize in Pymol. So you click here, a .psc file would be loading. You can open it in Pymol to visualize this in Pymol. You can also download and keep it as a PNG image. You can download the results in XML format. Here you have full tabular form of results where you can clearly see the residue, the amino acid, distance, ligand atom, protein atom, halogen bonds, hydrogen bonds, salt bridges. All this information is given here. So with this, we complete our traditional docking tutorial. We'll wait here for you all. So anybody has any questions, let me know.
I hope everyone has followed the steps and reached till Philip.
Please drop a thumbs up if you are done till here and you want us to move forward. Come on, everyone. There are many people here in the meeting. I can expect some more reactions. So we'll move forward with AI/ML based docking then.
Okay. Thank you all. Let's. So this is the end of the traditional docking. So next we'll be going for ML based docking. So let me share you my screen first. So as I have shared the GitHub repository link, you can click on that and at the by
I've
scrolling.
also pasted the collab notebook link here in the chat box. You can directly open it, or you can do it from your GitHub, as Rinku was saying.
Yeah, so you can right click it and then open it in new tab. So let us know everyone is at same page.
Everyone is here. Drop a thumbs up. Akshay, Ananya, Aniket, Deepti, all of you, you're here with us. Okay, Rinku, you can go forward.
Yeah. Okay. So before that, we need to upload the 3 files. It is already there in the downloaded folder. So as there are 2 folders, Autodoc Vina and ML, you can click on ML and then there you'll find 3 folders. And along with it, the files. So you need to upload 3 files: the predict underscore GCN, the requirements file, and train GCN. And say open. Yeah. After uploading, you can click on first cell, that is where it is showing the requirement.txt. So basically, it will install all the required packages. So as this is AIML based technique, which is integrated in the Autodoc molecular docking. So here, let me let me tell an overview of what all steps we'll be considering. So first, we'll be setting up our environment by installing all the machine learning dependencies. Then we'll be preparing the protein and ligand. So first, for developing a GCN based model, we need to prepare our training data set. So for that, we have provided an automatic molecular docking simulation. So where it will automatically prepare the protein and ligand files and then perform the docking. Out of that, we'll analyze the data, the doc results, and we'll extract the best pose, and then we'll provide this best pose for training the GCN model. So the purpose of training the model is to make predictions like binding energy prediction, as Husseina's explained how we get the binding energy. Like top 9 models are generated for each ligand protein complex, and then out of those, the first pose is the best pose. So similarly, here we'll be analyzing the result and get the best poses of the uploaded ligand. So as Husaina has demonstrated you guys with single docking, this automated script will perform multiple ligands docking at one go. So yeah, let me know everyone is at the same page. Everyone's installation is running.
Everybody here with us, right? So once the installation is done, you will be prompted to restart the session. So you have to restart the session.
So you can ignore this error. It is not required for now. Yeah, Hussaina, please continue.
Okay, so after you imported and uploaded your files, the next is we'll be importing Python libraries that we'll be using. So we'll run this code. So as we installed Autodoc Vina on our systems for traditional docking, we'll be installing it here also. So we'll say run. This will start downloading Autodoc Vina in our notebook. Once the code is done, we'll go to next, which is creating necessary directories. So we'll have a protein directory, ligands directory, and a results directory. So you can see it on your left side tab. Now we have to upload our files. So when you run the code, you see here that you have to upload a prepared protein file. So earlier we prepared the protein in PDBQT. Here we have provided you with prepared protein in the ML folder. So you say choose and go to protein and open protein.pdbqt. After this is done, you'll have to upload the ligand files. So choose files. Again, the folder will open. Go to ligand docking. There are two folders, ligands docking and ligands prediction. You have to go to ligands docking and select all those files present there. Control A, open, and all your prepared ligand files in PDBQT format would be loading. Drop us a thumbs up if you are here with us. You have reached till this step. If any error while running the previous steps, let us know. Yes. You can unmute yourself and ask your doubt if you have any doubt. Once done, we'll be visualizing the 2D structures of our uploaded ligands. So here we have 20 ligands uploaded. So you can see 20 2D structures. You can visualize them here. And then we'll be configuring our docking parameters. We made a config file while we were doing a traditional docking tutorial. So now we'll be doing the same. So we'll run this code. Here we have given a number of poses 10. In traditional Autodoc, it is 9. Here we have customized it. So it is number of poses 10. We have already given the grid box dimensions. And now we are running the code. Post that, we'll be executing molecular docking. So once you have uploaded your prepared ligand, prepared protein, you have made your configuration file, then we'll be executing our molecular docking. So you run it and the docking has started. So we did one protein, one ligand. It took approximately 1 minute. So we have 20 ligands now to dock. So it might take
Yes, sir.
15 to 20 minutes. So
Can
yeah,
you go back to the step where you uploaded the file?
yeah.
Yeah, so you can run this cell and then choose the protein file, which is present in the ML folder. So yeah, in the ML folder, within there are subdirectories. So for protein, you can select the protein folder and upload the single file which is present there. And later, again, after uploading this protein, you'll get another tab for uploading the prepared ligands. So you can upload it from here, the ligands docking folder, where 20 ligands are present. So meanwhile, if anyone has any questions or anyone has any issues, they can ping us in the chat box.
Yes, for people who couldn't, catch up with us in traditional docking, here you have time. You can definitely run this ML-based docking collab notebook. So if you want, I can repeat the steps again. So first we uploaded 3 files, which was predict.gcn, requirements.txt, and train.gcn.py. Then we ran all the cells one by one till we came to a cell where we had to upload our prepared protein and prepared ligands. So we had 20 prepared ligands and one prepared protein. All of that, when uploaded, we also ran the cell which prepared a configuration file where we had all our parameters, that is grid box dimensions in XYZ, and then we executed our molecular docking. So why are we doing this? The reason being that when you do the traditional docking, for each protein and multiple ligands, you have to dock them all one by one. But if you have a data set where you have lakhs of such ligands to dock, it is not possible to do it manually. And if you do it, it is very time consuming. And with the pace of big data, which is a thing now, and it is a part of biology as well. So we know that we can't rely on traditional methods, which are very time consuming and very tedious to do. We have these ML based methods. So we are docking these 20 now, and we'll be predicting much more based on the results we got from docking this 10 traditionally. So that is the goal, to let you know that if you have a data set of suppose 5 lakhs, you just docked 50,000 or 1 lakh out of it, and the remaining ones you can predict. And the prediction would take hardly 5 minutes, 2 minutes. 5 minutes, I have said, like more than that. So it is very less time consuming and it gives you quite accurate results. So that's the reason that we are learning about ML based, AI based methods for docking. You can also ask your doubts if you have any doubts which you encountered while you're traditional docking. Or in their ML based docking.
Also in future, if you want to train it on your own data, like you can refer this same script and then you can apply it on your own target specific data. So as Hussaina said, you can train millions of compounds at once.
Guys, you can unmute yourselves and you can ask anything, any random thing you want to ask or just discuss with us. Want to let know any specific parameter, any specific thing, you can just do that. It's an interactive session. Feel free to do that.
I don't think so. My docking cell is getting executed as I keep getting the error of Veena not found.
Okay, so like what command have you tried? The one which is pinged in the chat box.
Uh, yeah, checking files and directories, executing molecular docking. above that, everything else was sorted,
Okay.
like giving the dimensions of before docking. I've done till there.
So if you type just Vina, like VINA, and then press tab.
Wait,
Yeah. You can type the command like Vina tab, and then you will get the file name and space dash config and config.txt.
Yes, Rinku. Meanwhile, we have some questions in the chat box by Nilofer. So the first question is, by using Autodoc, we need to make PDBQT file, and then we can use it in ML docking. Even if you're doing ML docking, we have to rely on Autodoc for preparing PDBQT file, is it?
Yeah, so like as we have done traditionally, where we need to like provide only one single ligand at a time. So here what we are doing, we are automating the script so that we can train the generated data. So as ML based any approach, we need experimental data. Okay, so here as well, we are just training our preparing our data using Autodoc Vina on small set of compounds. So if you do traditionally, for say, if you have thousands of compounds, then you need to dock it all, like for say 10,000 compounds. So instead of doing that, out of 10,000, you can use for say 1,000 or small set of data for docking. So it will require less time for docking subset instead of whole set, and then use those as a training data. So yeah, we are even in any approach of AIML technique, we rely on experimental data.
But Rinku, can we prepare PDBQT file using our code also, or do we have to have those softwares for preparing the PDBQT files?
Yeah, as OpenBabel is command line based, so even there we prepare our ligands. So there are command line based tools where we can also prepare protein. So by writing single command, we can prepare our molecules and then upload it here. So there are different file formats as Autodoc provides us .pdbqt, like it is compatible with .pdbqt format. There are other formats as well like Mol2 or SDF. So there we can provide the particular format and then prepare the protein instead of manually preparing in the GUI of Autodoc Vina.
Okay, I hope Nilofer that answers your question. Akshay is asking, can we use traditional method for multiple target molecules for finding common drug compound?
We can like do the multiple target docking, but even there we need to prepare it manually. So yeah, it is feasible, but it takes too much effort. Instead of that, we can write a automated script. So for each config, like as we provided config for protein and ligand for single, we can create multiple config files for each target, multiple targets. So there will be multiple config files. As for each protein, there is different binding site. So we need to provide multiple config files for multiple target docking. So post to that, we'll be analyzing the results. Like I'll just explain it meanwhile it is running. So like analyzing the docking results, what it will do, it will extract the best pose from each dock ligand. So here you can see these are the generated output files in the results directory. So within each ligand file, there are 10 poses. As we mentioned earlier in the config file, it will generate 10 number of poses. So from each output file, it will extract the first best pose, and then also it will create a CSV file where it will paste all the best binding energies of each ligand. So that best energy will be used as a label for our regression model, that is the GCN model. So basically for GCN model, the AIML based model will be using features and labels, where features will be the graph embeddings. As I explained earlier, like it will read the structural representation of each molecule, the protein and ligand, and convert those into graph embeddings, where each atom will be represented as node and bond as edges. Along with these features, it will also consider the label that we are providing as binding energy. So the binding energy will be the best binding energy of the docked pose. Because as we need to do the predictions on the docked pose, like on the ligands. So it will give us the predictions as the binding energy results.
Also explaining you the gist of using GCN. So as Rinku said, so graph embeddings are graph neural networks. Basically, they have the simple principle that one thing is the node and the relationship between two nodes. Suppose there are two proteins and you're calculating protein-protein interaction. So the nodes would be the proteins and the interaction between them would be represented by the edge. So the edge is also an information. It is an informative edge. So similarly, if you imagine it here, the node here, one node is protein, other node is ligand, and the edge is basically the interaction, the one which we saw using PLEP, be it hydrophobic, be it hydrogen bond, and be it halogen bond. So that is how the ML model is storing information and training on the basis of that once we dock. So this is how this is working. The ML model that we have used is working. And convolutional neural networks, for that matter, they are best for working with image data. Here we will be providing data in the form of a molecular image. So it is a kind of 3D representation. So it will be learning from that. So it will be every pixel or every part of it would be a feature set, and that feature set would be given some weightage. Based on that weightage, it will be going to a next layer, and based on that, we'll be calculating what kind of interaction it has. So it will learn based on features, it will learn based on graph embeddings, and that combined is our GCN model, on which once we train, we can predict the remaining huge set of ligands based on the training set. If anybody is facing any difficulty or just inquisitive about asking something or discussing anything, knowing any tools, any other thing, you can just let us know. You can just unmute yourself, speak, drop your messages in the chat box. If you like it, you can give us some reactions that will encourage us.
Also, apart from GCN model, there are many such algorithms that we can use just for like developing a prediction model. So there are transformers, or what you can say, the LSTM models, where also it can generate the text base, or it will learn the features of the both ligand and protein. So such algorithms we can also use apart from GCN. Why we have used GCN here, as it is faster. So the training is faster in the terms of molecular docking. So once the docking is completed, I hope everyone is following the same page. Next will be the analysis part. where it will generate the CSV and extract the best pose. So the analyzed results will be saved in the docking outputs. So if you expand this, there you can see the best pose directory where all the best poses are saved. So basically it will select, it will contain only one single ligand, which is the best ligand orientation. And there is this CSV. If you double click on it, you can get the overview or the summary of all the ligands and their binding energies. Like these are the 10 binding energies, and out of these, it has selected the best, which is the lowest. So this column will be used as the labels column for training our model. So next will be, you may download the results for visualizing it in the PyMol, like how exactly the docking is done, and also keep it for future reference. So I'll be skipping this part. It's optional. Then further, we can go for Philip docking analysis. Like as we saw, we need to go for a web page and then upload the ligand. And first, beforehand, we need to create a complex manually. So here, the Philip provides a command line based tool as well. So before that, we'll need to install PyMol. So even PyMol is available in command line based interface. So this might take few minutes to install. So the overview of this Philip analysis is that we'll first create complexes. So the best poses which were extracted, it will be used for creating complex with the protein that was uploaded earlier. So now that we have 20 poses, it will generate 20 complexes in .pdb format.
Rinku, can you open the docking results.csv and show
Yeah.
how does it look?
Yeah. So it will show the summary, like what ligand input was used, what is its output file, and then their respective binding energies, and out of those, the best energy.
And this is for each prepared ligand file.
Yeah, so till now 20 were done. So you may see 20 sets of the ligand. Let us know if you have any questions.
So everybody, sir is here. So if you want to ask anything, sir would be here to guide us. You can unmute yourself and feel free to ask questions.
Yeah. So once the installation is done, the session will restart automatically, and then next we'll need to create complexes. So here you can see it is creating complexes. So as we provided PDBQT files, it will convert using OpenBabel and generate the complexes. So basically here, like all the structures are will be readed by a package called rdkit. So it will be even that is command line based. So it is reading all the molecules. So after creating complexes, we'll be executing the plib. So even this is automated. So it will, by clicking just one run button, it will generate all the 20 complexes report file of plib. And its result will be saved in plib report directory. So here you can see for each complex, it has saved the directory where you can, where there are subdirectories. There is PSC file, as Hosseina explained earlier, mentioned earlier, like we can use this for visualizing it in PyMol session as well. So here you can see the PNGs are generated. Like for each complex, it is showing the binding interaction.
Yes, so again, you can see the hydrophobic interactions, hydrogen bond interactions. So, yes, and there will be a summary file also, which will give you the summary of bonds, and also for each ligand also will be getting the file and reports.
So like for each ligand or complex, it will generate .txt file where different types of interactions will be mentioned. For say, if I have hydrophobic interactions, at what residue number of the protein it will bind to what part of the ligand, and all the other mathematical values where it will calculate distance, then its coordinates. So similarly for hydrogen bonds, and there are even more interaction types. So once the Philip profiling is done, we are now all set for training the model. So the script which was uploaded earlier, the train gcn.py, it has all the scripting where it will create a architecture, read all the uh, data set, like the best poses and the label, and will train the model with that features. So as this is just a prototype, we are considering a small set of compounds, like say 20, but even in real life, like we need to provide a large data set to get accurate results. So here you can see it has executed for 200 epochs, like for 200 times the training data was iterated for learning, and then it will provide us the evaluation results where we can analyze the performance of the trained model. So as this is a regression model, we'll get loss functions such as root mean square error, R square value, or we can say correlation coefficient. So the standard value to consider this is, for say, if we want a best model, the value should be the error of these three matrices should be less than 0.5 or even more closer to 0, which are acceptable, and the R square should be closer to 1. So why this result has come? Because we have used a small set of data, and even like just to create a model, it needs more optimization for developing best accurate results. So all the model output files, the PNG and evaluation matrices will be saved in model output folder, where you can see the predictions. Like as we have splitted the data, it will predict the values. But as it is small data, we have to consider the closest prediction, like there should be no much difference between predicted and actual value. So once the training is done, we'll go for predictions. So as we'll be predicting on new set of ligands, we need to upload new set of ligands. If we execute this cell, it will say to upload your PDBQT files. So you have to choose the files from the ligands prediction folder, the second folder which is provided. So here we have around 180 compounds to go for predictions. As it is ML based, it will predict the binding energy in few minutes. So let me know anyone is facing any issues. So basically, to get optimum results or best predictions, we need to train the model again with a large data set. So for now, as it is just a
Yes, so
toy,
it is a toy example. So
yeah,
when you train the model with a large data set, it learns many more features. So if I explain this in a very simple, with a very simple example, so suppose if you have to train a model to, so that it recognizes a particular object. So you'll have to give it a very large number of data set for it to train so that it accurately, recognizes only that object and not similar objects or similar looking objects. So the more accurately it predicts is defined by how much better training data you have provided it. So good quality training data and large number of training data sets are required for your model to work better. So here this is a toy example. So I have trained it for just 20 ligands and we are predicting 180 ligands, but you can train it on lakhs and predict many more. So this is how ML based docking works. So it saves time. Yes, once it is trained, you do not have to train it again and again. You can just keep predicting. Yes, but for every new, protein and ligand interaction or docking, you'll have to train it again. Like you have trained it for one protein and you expect that you can just extend it to a different protein. That won't happen. You'll have to train it for every single protein you want to predict. So that is how it will work. But for one protein, once you have predicted, you can do n number of like once you have trained, you can do n number of predictions. So there is no limit to it.
so basically it will save the train model in .pt format. Like this is our best model till now. So if you have any other target specific data, you need to train it again with that and generate a new model.
I hope everyone is following. Is anyone lagging behind or require the assistance? You can uh, unmute yourself and let us know. We'll help you out.
So as we can see, like for one single docking, it took around 1 hour, but here we are predicting around hundreds of data. Yeah, so now the files are uploaded and it's time for predictions. So you can see it is reading and processing all the files which were provided and also predicting the binding energy. So here you can see for a particular ligand, there is this predicted value. So you can see how fast it has done the predictions. So yeah, so predictions are done, and you can see the 188 files are successfully processed and the predictions are done. Even you can see the top 5 predictions. Also, it will save a predicted CSV file where we can visualize. So here you can see it has done most of the predictions with all the past ligands. So after these predictions, we can, as we saw, like we can apply ADMET analysis, more filtration criterias. So here is one of the criteria where we can filter our compounds, the predicted compounds, with a standard value of threshold. Like if we have a co-crystallized or standard compound, we can consider that binding energy to set as a threshold and filter the compounds which has lower than that threshold value. So here we can adjust the values according to our standard value. So if I say I have mentioned -10 and click on submit, then I have found 163 compounds out of 188 compounds which has the binding energy less than -10. So here it will save all the compounds to SMILES format, as ADMET AI analysis requires SMILES as an input. So here you can see it has successfully saved 163 compounds, or we can say it is narrowing down the specific compounds which shows similar properties as those which were trained earlier. So once the filtration is done, we can go for ADMET analysis. So before that, we need to install ADMET AI tool. Even this ADMET AI tool, which is used for predicting pharmacokinetic properties as well as physiochemical properties, it will require, it is based on command line, like it is command line based tool. So even we can run this tool with a single command.
Okay, so just a very basic question every one of you should get here is why we are doing ADMET analysis and what is its importance. So if suppose you have you are in very early stages of discovering a drug, so we are here to learn AI in drug discovery, right? So when you're discovering a drug, you'd also like to know how the drug behaves once it gets into your body. That is the pharmacokinetics of the drug. So the absorption, the distribution, its metabolism, excretion, toxicity, which is the full form of ADMET. So that is a very important parameter while designing a drug. So once it passes these parameters, then we can go for later stages of drug development, which includes clinical trials and etc. So ADMET analysis is one of the important things to keep in mind while we are, going for drug discovery. So once you have docked, you have found like good compounds according to your docking results that these are binding properly, they have a good binding energy, but still we need to do ADMET analysis. So we have a question.
Okay.
When do we do ADMET analysis for drug discovery? Before docking or after?
It depends on the pipeline. Like it is a good practice to do ADMET analysis before docking. Like it will, if we have standard molecules for say 10 to 15 molecules or even single molecule, and we have its ADMET results, so we can screen thousands or millions of compounds based on that threshold values by keeping the standard values, the parameters which the standard compound shows. We can consider that and filter compounds. and then later go for further docking. Or else we can dock the compounds with the standard like the reference ligand and screen based on that binding energy as well, like keeping the binding energy as the filtration criteria. So it depends on the study, like if you want to go for docking first and then admit analysis, and then or else we can go for admit analysis first and then docking. But these two are critical steps to consider.
I hope that answers your question. Yes, any more questions, doubts, can let us know.
So even in this our workshop, we'll be like doing admit analysis and then again dock the filtered compounds later. So after installation of admit AI, we'll need a restart session. So it will like don't show any compatibility error. So further after installation, we'll run the admit AI tool on the filtered compounds, the 163 compounds that were filtered. So even this tool, it it just it is faster than any other traditional admit analysis tool. So it will do predictions in shorter period of time. I hope everyone is following the same page. Yeah. So you can see within seconds it has done the admit analysis. So the results will be saved in admit results.csv. If we open this, we'll get a different parameters. So for each ligand, it has different properties. For say these are Lipinski rule of 5, then the admit properties, absorption, toxicity. So these are all predicted in shorter period of time. So here you can see for each ligand, it has written the SMILES format. So this is basically the SMILES format that we need to provide it to the admit tool. So as we mentioned earlier, OpenBabel is the tool where we can do the file conversion of molecules. So once the admit analysis is done, we can more consider filtration criterias. For say, we have seen admit analysis properties, the admit properties. So if we execute this cell, we'll need to provide the threshold values. For say, if we want molecular weight, which is less than 500 Dalton. So for now, I'm keeping it default. You can adjust the values. So here, based on, we can consider standard values as well to filter the molecules.
Okay, so here the values we are getting, which Rinku says is the standard values. Why they are standard is for drug likeliness. There are some rules which are made. So Lipinski is one of them which we are using. There are Weber. There is other rules. There are companies, big pharma companies, who have defined their own set of rules, which they use for predicting and like deciding drug likeliness. So here we are using Lipinski, and Lipinski says that molecular weight should be less than 500 Dalton. Okay, log P should be less than 5, and like donors and acceptors, all of them. So it has defined. So that's why the standard values are like that. So those are standard values for any other admit analysis. Also, if you are using Lipinski rule, if you change the rule, then the parameters also change.
Yeah, so for now we have considered these parameters. You can even add on more parameters according to the specific study. So once the filtration is done, we can see we have got around 6 compounds here. Like 6 compounds are filtered, which shows best parameter values. So you can see here the 2D structure of the filtered compounds along with the properties, corresponding properties. So once the filtration is done, we'll need to dock it again. So here you can see instead of 188 docking, we have come to the 6 compounds docking, as we have considered all the parameters by filtration criteria. We have considered all and then narrowed it down to 6 compounds. So till now we can get 6 compounds as the potential molecules to the respective target. So let's execute the docking for the 6 compounds. So this is how it will save the time, like filtering the thousands of molecules and then docking for a small set, which are showing potential properties.
Yes, and apart from time, this is also storage efficient, like to download softwares on your system, to keep all the files on your system, run traditional docking, again save the results, and do further post docking analysis, again save the results. All of this can be run, saved on the cloud. So this is how it is storage efficient as well as it is, you know, less time consuming, and it is more interpretable. Like you can easily interpret, like we gave input of these many compounds, then we predicted these many compounds, then docked these many, then post docking we analyzed and then further shortlisted, and then finally we have 6 and then ran docking on those. So it is easier in every sense, and also it is much better to go with AI when dealing with big data, which is a thing now, as I already mentioned. So AI is already here and or incorporated in every sector, including biology. So hence this workshop brings to you a toy example to give you a gist of how drug discovery industry will be revolutionized in future using AI ML based approaches. So the virtual screening would become really easy. So much more virtual libraries can be screened, much more drug targets can be easily, brought into attention in much lesser time. So we, as we already know, as in our morning session, we know that how discovering a drug is not a short duration process. It takes years from starting till end. So we can't, go faster with clinical trials as of now. But while virtual screening and with computational methods, we can make them more faster, more efficient to at least pass that first stage to get a lead molecule and to get optimizing lead molecule that becomes easier for us as computational chemist and as computational biologist.
Yeah, and also like for this workshop, we have considered only a small example. There is much more to explore. Like instead of like there are many tools, AIML based tools, which are completely AIML based tools. Not even like they consider the traditional docking. Even those are showing much accurate results. So, like in the future, if you are interested in joining our course, so we'll like demonstrate you all the AIML approaches, how we can create a model architecture, or how a complete tool can be created. So such advanced level can be also uh, like explained to you guys in the course.
Guys, you all are here with us, right? So you can definitely interact with us. You all are with us at the same step. Anyone is lagging, anyone is requiring any help, anyone wants to know something more, something less, let us know.
So the docking results will be saved in the filtered docking outputs. So here you can see the best pose for each ligand is been saved. And along with this docking, as we have done predictions of these results as well. So here you can see how accurate, like with even a small data, it is showing like closer results. So this way we can test our model as well, like whether it is uh, like predicting the correct value or not. So here you can see it is the best energy, like the docked uh, energy, and these are the predicted energy values. So you can see for the first entry as well, it is showing closer results, -10. For rest, it is like not much difference. But to improve this model, like to get more closer results, you can optimize the model by hyperparameter tuning and all other optimization methods and increasing the training data set. So once the docking is done, again, we'll analyze the post-docking analysis using PLIP tool. So here again, we'll create the complexes, which is also automated. So it will create the complexes for all the 6 ligands with best pose. And the results will be saved in the filtered PLIP complexes. So here, the same structure is saved, the PDB format, and then later we can execute the PLIP tool. So here it is executing the PLIP. So if you see, we have automated this script. So it is running this tool using single command, like this one. So for each command line based tool, we have automated script where it can process multiple complexes. So here you can see and also visualize it in the PyMol. Yeah. So in PLIP report, you can see the same structural data structure where it has saved the .pac file. So let me just download one single example, like how to analyze the PLIP interaction file. So here we are at the end of the stage. Let me just open the PyMol session file. So this was the last step of our workshop. How to analyze these, I'll explain. It's optional. You can even visualize it yourself by downloading the result. Even here, you can click the download all results button where you can download all the results at once. I hope everyone has executed their last step.
Yes, you can write in the chat box whether you have executed your last step. So all of you, we'll be visualizing the result in PyMol. And also, I would like to inform you all that post our session, we'll be joining back to the link which we were using earlier, like for our lecture sessions. So there will be a short combined meet for you all where you'll be filling the feedback forms, and based on your entries in feedback forms, you'll be filling the feedback forms with your names and affiliations, everything. You'll be dispatched your certificates. You'll be provided with your certificates. So I would like to request you all to be available in that common meeting. Yes, so
So
we
here,
are towards the end of this session.
yeah, so this is how the Philip interaction file looks. Like here, you can see these are all the residues of proteins which are interacting with the ligand. Even by this, we can label what amino acid is interacting with what part of the ligand. So if we select label, we can mark those label. So here you can see all the amino acids which are interacting with the ligand. So yeah, this is the end of the workshop. So yeah, thank you for completing it with us, the workshop. Let us know if you have any questions. Feel free to ask.
Yes, sir, I would like you to give them some insights about how this will help in drug discovery, easing drug discovery process, given that discovering a drug is a very challenging task and you need to be very specific before a drug, from your library goes to market. So how AI/ML would accurately be a part of the already existing drug discovery process? Sir, can you hear us?
Yeah, this question to me.
Yes, sir.
Hello,
Yes.
can you hear me?
Yes, sir. We can hear you.
Sure. Actually, my internet is very slow and there is no power this morning. So, okay. Uh, so, yeah, that is that I mentioned in the first session talk. That is AI machine learning will take over this field for designing or identifying or optimizing the molecules. It will be the next generation level of drug discovery. Uh, in target identification, lead optimization, preclinical, even the analysis of the data in the clinical trials also, the AI are massively used. So if you look in different papers and all that, that is a lot of success stories are already there. The different companies are already used
Yes, I think there's
the essence of AI
so there's a lot of lag in your
learning,
voice.
and the molecules are already in clinical trials or like that. So definitely it will help, but you need the training, you need the expertise so that it will actually you can implement according to you. But it is a continuous process. You have to keep learning. So that is there. Okay.
Yes, sir.
Someone asked that is can you have like this for a session? Yeah, definitely. Yeah, actually, I said that my internet is very slow. Yeah, in the future, we'll definitely. Mm. Okay, so Rinku, just everybody should join in the previous link, and there
Yeah.
will be a feedback form. So after that, you will get the certificate. So please, once it is finished, you come back to the
Sure, sir.
original session.
Okay, so let us know if any questions are there regarding this workshop, or else we can jump into the combined meeting.
Okay, if no more questions, we can join the common meeting.
Yeah.
Ringu, can we drop the link again in the chat box?
Yeah, sure.
Yes. Yes, so the meeting link is in the chat box. Let us see you all there.
Yeah. Thank you, guys. Thank you for the patience.
Thank you. Thank you for listening to us patiently. We'll meet you soon with some new workshops, okay? Thank you.
Yeah. Hello. हाँ था तो यही. Rejoin the morning session link for final session. Yeah, same है. कैसा गया? कैसा था? Okay.
So this is group 4, no?
Yes, sir.
So, how was the session actually? I would like to know from the participants. You may unmute and you may. Everybody, just for your feedback. Am I audible?
Yes. Yes, Ananya, can you like answer this question? I really saw you were very interactive during the entire session, so it would be nice listening from you. How did you like the session?
Yeah, ma'am. It was very easy to follow your instructions, especially the Google Colab notebook was very helpful. We can refer to that later as well. And the other manuals that you provided were very helpful. And it was easy to follow through both of your instructions given, both traditional and ML method. Thank you.
Okay, so your background is, drug discovery, or
Yes, Ananya, that's a
Ananya?
question for you.
Sorry?
Sir is
Do you
asking
have a
about your
background?
background.
Yes, sir. I am from Biotech and Bioinformatics. I'm currently pursuing my MSc in Biotech and Bioinformatics from IBAB Bangalore.
Okay, okay. So you know a little bit about, okay. So you got the idea about machine learning, how can apply in docking, am I right?
Yes, sir. ML was new for me. It was interesting.
Okay. Anybody else? If whatever the feedback that is, I would like to just know that will help us for the next workshop. Keep in mind.
Yeah, so you can tell us the suggestions, what we can add more, or in what field you are interested to take workshops on.
Yes, that would be
Okay.
interesting to know.
So actually, this sorry, I'm not getting your questions. Hello, audible?
Yes, sir.
Yes, sir. Sir, you can keep your video off, else it is lagging very much.
Yeah. Oh, what? You asked something to me?
Sir, we were asking to the participants like what more interested fields you would like to attend the workshop on. So
Exactly. So this one-day workshop is not sufficient to give a complete idea, but we try to give the importance, and only one approach we have tried to cover, but still, since it is online and also uh, this is actually a lot of issues are there, and this is a time constant also. But definitely, we'll try to conduct more in future, and definitely, if you want to pursue form, that is advanced
yes, Gokul, you can
diploma.
unmute yourself.
Yes, Gokul, you can unmute yourself and let us know what you want to ask.
So what sir is telling is
I
like,
think.
um,
Yeah. Go ahead.
yes, sir. Like, as your voice was speaking, I was asking people like,
Yeah, Gokul, yesterday you talked about this protein preparation, ligand preparation. So is it clear to you?
Okay. So can you hear me?
Yes, I can hear you. Tell me.
Yes. So we have a suggestion that we should bring a workshop on next generation sequencing techniques and analysis.
Yes, definitely. Definitely, one by one we'll do. So we'll keep in mind we are for your suggestion and definitely will do. So keep updated through our LinkedIn page. So apps in design, yeah, uh, in all the field. So we have our bioinformatics section and AI machine learning section, drug discovery. So one by one we'll do. We'll have plan for this vaccine design or maybe bioinformatics thing that is there. And also, Nilofer, we'll conduct something like healthcare sector. How can we predict? How can we apply AI machine learning in radiology or the orthopedics and all these things? So that also will do. Yeah. Thank you, Natya, for your.
Yes, so Gokul, you said the workshop was very useful in your project work. So here is an opportunity for you. If you want to discuss anything more, sir is here right with you. You can go ahead and ask questions, discuss more. That's a golden opportunity for you. You can learn even more. You can also let other participants and let us know how it helped you in your project. Would you like us to give you any more suggestions, insights? Also, anybody else who would let uh, you know let us know how their experience went overall, and any suggestions, any more workshops you need, and the topics on which you need the workshops, drop us a text in the comment box.
I think group 3 and on 2 and 4 turn. Not 3, they are actually almost done. So let them join. Rinku, you can also can add, huh? You're the sign offs. Yeah. You're co-host, right?
Yes, sir.
Hi, Atul.
Hello, sir.
Yeah, how was the workshop?
It was good, sir.
It's good. Okay. I think a lot of students from your college joined, am I right?
Yes, yes. Sir, the students are also know, means they also wants to know how the AI will help to design the drug and the types of different softwares are there.
Okay, okay, okay. So, your students are here?
Uh, I think not, sir, because their exam is there.
Okay,
Semester exam is ongoing, sir.
okay, okay, okay. If all groups are here, please let us know. Uh, Sumbul, are you here? Sumbul? He's not here, no?
So basically, this was just a overview of one small example. We can also we are happy to conduct more advanced level of workshops. Sorry, your voice is breaking.
Naima, might be my laptop.
Yes, sir. Okay, sir. I'll carry on. Yes. Uh, yeah. So, one feedback form has been shared with you. The link has been shared. So I request everyone to please go to that link and please give your genuine feedbacks for the improvements, positive points, negative points, and whatever you feel you need improvements and would like to see more on which topics. Please go and submit your feedback on that particular link. Also, talking about the certificates for the workshop, it will be provided through the mails which you have submitted. So after filling this form, there I guess there's an option to enter your email ID also. So there you can submit your email also, and then you will get your certificates there. And if somebody was asking one question that can I know if I'm working on a multi-drug resistance disease, what drug? Okay. So address you, Akshay, you want it through a AI ML approach kind of a thing? You want to know it, or what exactly you want to know from this?
Okay, so I can try to answer that. Okay, so suppose you are, trying to work on a disease like TB, which has like MDR TB, which is multi-drug resistant TB. So drugs for which the TB has got resistant, you'll have to identify that drug binds with which protein, and then you'll have to study the interactions. So when what interactions are causing the drug to become resistant? So there are mechanisms of any drug to become resistant. Like, for example, the drug is binding in such a way that the ABC transporters are throwing it outside of the cell instead of drug influx, it is causing drug efflux. Okay. And there are many such other pathways for drug resistance. So you can study those pathways to know what can be the possible way by which the drug is resistant. So you can go for sequencing data. That's one approach. There can be other approach also. You can study for mutations, and then post study of mutations, you can find if those mutations are found already documented in databases, and then associated clinical implications if they are causing drug resistance, and then possibly you will get towards the pathway by which that drug is resistant. So that can be one approach if you're going by mutations.
Okay. Any other questions and queries from anyone? Okay. Yeah, people who have joined late, I will again share the link of the feedback form. Please go to this feedback form and submit your feedbacks. Yeah. So with that, we have come to the end of the workshop. We had a very good session of lectures and followed by the hands-on training. People with different backgrounds have came up and explored this. So yeah, SilicoScientia is very grateful for your time, involvement, and patience for believing in us and joining in good numbers. Yeah, so thank you all for joining the session, and we will be looking forward to more such workshops in future. Yeah, thank you all. Yeah. You guys can I guess leave the meeting then.
Hello, ma'am.
Yeah.
Hello.
Yes, Indranil.
Ma'am, do you provide means on online free internship for PhD scholars or master student if they are exploring for project right now?
We advertise internships time to time. If you're talking about free internships based on what is your study design, your project, and what capabilities you have, maybe we can go and take a interview kind of a session too if you want to continue or you want to work with us. So yeah, you can just mail your project design and what you're looking for so we can think of it.
Yes, ma'am. Thank you. Ma'am, can you drop the email, please?
Yeah, I'll just drop the email here.
Thank you very much, ma'am. And thank you, team.
So yeah, this is the email for any queries, and if you want to reach out for anything, you can just mail to this email ID. Yeah, thank you everyone. Yeah, so with that, I'm happy to announce that we will end this session. Thank you.